I want to tell you guys a little bit about the Doppler shift. You might know a little bit about it, but I want to sort of flesh it out some more.
Yeah, that'd be good for me.
You've surely heard of it. This is the shift in the frequency of sound between when an object is approaching you versus when it's receding. We know it intuitively. That's the fun part about it.
Yeah.
Even if you didn't know there was a word for it, we know it. Because, for example, if you're on the side of a freeway or even at a racetrack, there's the sound of the car as it approaches you. And it goes, and that's different from the sound it makes as it recedes from you. It goes, and you put them together, you got, okay. That's what happens.
See, I know it because there is a meme of you giving a talk and doing that. And as soon as you do it, they show a hurricane and a sign that knocks a woman.
Today and yesterday.
What? Stop. Okay. I've seen one of those memes where somebody loads a fish into a cannon and then shoots the fish, and then it goes meow, and then it lands in a fish shop somewhere.
Yeah.
So I didn't know that
But the one with you is hilarious.
Having never grown up near a NASCAR track or a racetrack of any kind, I would know what you've just described from aircraft that would fly overhead.
Yeah, it'd be easier at an airport. You'd get more of that. Yes. Okay.
Yeah.
So the point is, if I recited that Doppler effect sound differently, you would say, "What's wrong with you?" Right? If I went, no, you know intuitively that that's wrong.
That's true.
Or no, it's stop laughing at my Doppler shift.
It just sounds like a car going by with a cat hanging out the window. That's having the time of its life.
I think Chuck is jealous because he wishes he could do the Doppler shift.
So Neil.
So here's my point. Here's my point. So it turns out that the frequency of sound that is actually being made is accurate only when the car is directly in front of you, passing by. Okay. So when it's coming towards you, the sound waves are compressed, which puts more crests and troughs by you per second, more wiggles. And if there's more per second, that's a higher frequency. That's what frequency is. How many crests per second?
Yeah.
So higher frequency sound, another word for that is a higher pitch. Okay? As it's receding from you, each next sound wave is now stretched from the previous one. And so that's a lower pitch. But if it's right passing in front of you, it's neither coming towards you nor away. So the only truly accurate signal you can receive from the car is right when it passes in front of you. Just a point of information there.
So what do we do with electric cars?
Okay, it turns out that not all of the sounds you hear is the engine.
No.
Right.
Okay? And in fact, depending on how fast the car is going, in some cases, most of the sound is the air passing over the car and the sound of the wheels turning
on the track.
On the track. Those make sounds unto themselves. Now, those who live in Los Angeles, okay, there's an In-N-Out burger joint right beside LAX.
There is.
And it is right there in the approach for planes landing. And you sit there eating your burger and you just watch it happen. The sounds you hear, the plane does not need engines to come in for a landing. It's basically a glider at that point.
Yeah.
So if you want to know, yes, the engines, they're on, and so they're making some sound, but that's not the dominant sound. If you want to know what a pure airplane sounds like, with air going over the airfoil, it's what the planes sound like as it's a very high pitched sound. It's like Chuck, I can't get it. It's like yes.
Yeah.
Good one, Chuck.
I used to work at that In-N-Out burger. So
Can you imagine this burger joint, right, by LAX? It's packed. to the rafters with aviation nerds.
Oh, well, they better come sponsor a show. Let me tell you that. So the point is, we're talking about this because of NASCAR. All right. So now I've been to a couple of NASCAR races in my life. Okay. One of them was at Daytona.
All right.
In Florida, FLA. Okay. So I was so disappointed. You know why?
Why?
They have speakers all around the track. So you don't get the pure sound of the car moving from your left to your right. The speaker is giving you the sound of the cars as they are, not as they are Doppler shifted towards you and away from you.
Wow.
So you're actually missing the most beautiful Doppler shift you could possibly have, and that's a 200-mile-an-hour car coming towards you and going away from you.
Screaming at you as it goes
Screaming
around.
at you. Can you imagine how high that frequency would be?
Yeah.
At 200 miles an hour, and how low it would be going out the other side. And they got some loud-ass engines on those. So you get the airfoil noise, the track noise, and the engine noise.
But if you're in the crowd, Chuck, and you've got these PA speakers around the track, it is literally a constant wall of sound.
It's constant. That's correct.
So therefore they don't lose out on this sound when the cars are on the far side of the track.
So I think that might be the motive.
That's probably why they do it.
And I've only been to those couple of tracks, so I can't speak for Talladega. I don't know, but so I was so ready to just feel the Doppler shift, and it wasn't there. So the best way to do it is
they do that on the televised broadcast. If you watch the televised broadcast of NASCAR, what you hear from the wide shot when you're looking at all the cars is, and that's it.
Yeah.
It's just a constant hum.
It's a constant hum.
The only time you hear the Doppler is it's a single camera in the ground and the car goes by you.
Okay. Right.
See,
right.
Chuck is really into NASCAR, isn't he? You could tell this.
I got to tell you, as much as I make fun of it, sometimes I do like watching it, but not as much as Formula One.
Nope.
All right. We'll start that fight here and now.
Yep. Here we go. Get those racing overalls off. Here we go.
Put that jumpsuit on. Take those overalls off.
Right. So Doppler traces back to a German physicist. He might have been a chemist, actually. A German physicist, Christian Doppler. And he first measured this. And you do it.
Did he have a twin? Did he have an identical twin?
No, that was Einstein with the twin paradox. So...
Yeah. No, I'm just thinking of doppelganger.
Yeah, I was going to say it was Christian Doppelganger.
Doppler ganger.
Thank you. Thank you. Chuck was there.
Leave Chuck to tell the jokes on this one.
All right.
Gary, you are not hired to tell jokes. Okay?
Apparently not.
So he did it with a train, a railroad. That's a big thing. It's on a track. All right. You're doing this before you had automobiles. This is in the 1800s.
Right.
And so what are you going to use a track? And it was some years later where, forgive me, I forgot the guy's name, who decided to do this with two orchestras playing on flatbed rail cars. And each orchestra was told to play exactly the same note as, it's a subset of an orchestra, as the other orchestra. Okay. So they each are playing the same note and they're coming towards you. Okay. And so you hear so the funny part is as they pass in front of you, you hear the note, but all the notes were higher pitched as they came towards you and lower pitched as they went, yet you know they're playing the same note. That's what they were instructed to do. So this was the people's fascination with this phenomenon. And I mean, it was quite the discovery. And by the way, this extends into the universe. We look at light shifting because objects moving towards us or away from us. And we can determine exactly, so I didn't make it clear. Does it make sense to you that the amount that the wave shrinks or the amount that it expands should be related to the speed of the object? Are we together on that?
Yes.
Right. So the faster it goes, the higher the pitch or the lower the pitch, but that each of those would be more with a higher speed. It turns out there's an exact relationship between the change in frequency and the speed, and it's the Doppler formula.
Okay,
You
so what
plug it
happens
in.
if I break the speed of sound?
Oh,
Am I now ahead of? Oh, steady. Don't get too excited.
Right.
so
Well, in that case, the note being played bursts your eardrums.
you dissolve into a pile of goo.
Pile of goo.
All right, so here they are coming towards you, and you have this frequency that is broadcast, and the moment because the sound speed is sort of the same in air, except now you're moving through the air. So the next crest is compressed relative to the previous one. If you keep increasing your speed, the wavelength gets smaller and smaller and smaller. The frequency gets higher and higher and higher. The pitch gets higher and higher and higher.
Right.
There is a speed with which the next wave lands exactly on the wave you just emitted moments ago.
Mm-hmm.
When you are doing that, you are traveling the speed of sound, and every one of your waves is on exactly the same wavefront. So there's a focusing of all of the sound that came in front of you into one place. And that place is a shock front moving at the speed of sound.
So that's your sonic boom?
That's the sonic boom.
Wow.
There you go. There you go.
So what if I floor it and I go faster than the speed of sound? Do I then dismantle the Doppler shift?
Okay, so the Doppler formula works only up to the speed of sound.
Right.
Okay.
After that, it doesn't make sense to talk about a frequency because everything is jammed into. There is no. It's just a cacophony. Right. So it's what we call the linear regime of the phenomenon is where the Doppler formula applies.
Right. Wow.
Yeah. So I think because if you can't get it at NASCAR for the reasons I described, then walk up to the side of any freeway, and you hear. And of course, you can tell which are the electric cars and not, because one will have an engine, but they'll all make sound. Every one of them will make sound.
That's good to know. Next time I'm selling oranges, I'm going to actually try this out.
Oh, is that how you supplement your income from Star Talk?
Listen, I get out to the Major Deegan here in New York City.
Okay.
But, here it's
the Major
mango.
Deegan's Interstate 87.
87. Yeah. By the way, in New York, it's mangoes. In LA, it's oranges.
Okay.
Yeah, people sell mangoes on the freeway here, which is so weird because it's a tropical fruit and we are nowhere near the tropics.
Don't worry, we will be soon.
Oh, that's another episode.
Excellent.
Yeah, so all right, so I just want to throw some Doppler shift out there.
All right.
Maybe you knew about it or you didn't, but those are the details. And it applies to trains and orchestras and objects that move throughout.
I want to know. I want to know who it was. Put an orchestra on two flat big rail cars. Right? Was it Count Bont loaded? Count Bont way too much money.
Wait. Let me get. Well, I know who it is. Hold on.
All right, please.
I'm getting this from a book that is coming out this fall. It's the third installment of a Star Talk book in a collaboration with National Geographic.
Very nice.
It's a book I've co-written with one of our senior producers, Lindsay Walker.
Fabulous.
So CHD Boys Ballot. Interesting name there.
Wow.
Conducted a simple yet brilliant experiment to demonstrate the Doppler effect to anyone in doubt. By the way, the original Doppler effect was described just a couple of years earlier, 1842. So he positioned one band of trumpeters on a train platform and another band of trumpeters aboard a train to pass them by. And both were instructed to play the same note at the same time. And so then this whole thing was observed by all the curious onlookers. So yeah, it's a fun thing. But by the way, remember I told you the change in frequency is your speed in a formula? This is what radar guns do with the police.
Right.
They boop you with a radar gun and they're looking at the change in frequency of microwaves that are reflected off your car. So if your car absorbs all microwaves, the cop will have no signal back to them, and as far as they're concerned, your car isn't even
What
there.
if I cover the whole car in aluminium foil?
The aliens will not be able to read your thoughts.
You'll be safe.
You'll be safe.
Yay. Who doesn't want to be safe?
So, but if what you put there reflects them back, then it works in the favor of the cops.
Yeah.
All right. So the point is they can get their most accurate measure of your speed if they're standing exactly in the middle of the street as you drive towards them.
They have to be directly in front of you. If they come on an angle, then it's all
to get the correct speed, correct.
Yes.
But they're not in the middle of the street, they're on the side somewhere. Or if they're clever, they're on a turn, and right before the turn, you are driving directly towards them. Yeah. But typically you're on a straightaway, okay. Yeah. And so if they clock you speeding and they were not standing right in front of you, you were speeding. Because at any angle from being directly in front of the car, there's a cosine diluting of the speed that they measure. So if they're at an angle to you and they clock you going 100 miles an hour, you were probably going 115 miles an hour, but you still get the ticket. But they can't ticket you for 115 because they didn't measure that. That's the point.
Right. See, and that's why I have a problem with them doing that to the black NASCAR drivers as they go around the track. I'm like, why are you shooting him? Why are you shooting him with a radar gun? That's the only NASCAR driver to ever
get a speeding ticket.
Lights and sirens go off. Woo! Woo!
Chuck has an active imagination here. So all I'm saying, by the way, there's a whole other in principle, there's a way to thwart that invokes laws of physics that relate to your car, but that's for another day.
Okay.
And plus, I don't think I should be giving instructions on how to break the law.
Okay. Why?
I think a lot of people listening right now have Chuck's question on the tip of their tongue. Why?
I'm confused. Like you'd probably be the only person I would take advice from on how to break the law, because everybody else I know is too damn stupid.
What it comes down to is at any moment, no matter how fast you're going, there is a part of the car that's not going forward at all.
Ooh.
Okay.
Maybe I should save that for another.
You damn sure should, because that is insane.
Oh, okay.
That's a teaser.
All right,
that's a teaser.
That's a teaser. I'm going to dangle that in front of you. Okay. All right. And for some trains, no matter their speed, there's a part of them that's moving backwards while they're going forwards. So
are you just messing with us now?
No, it's true.
I'm just true. Like, yeah. And I believe for that car, you have to have a flux capacitor. Wow.
Well, there you have it, guys. An explainer for Star Talk Sports Edition. Chuck, Gary, always good to have you there.
Always a pleasure.
All right. Neil deGrasse Tyson here, as always. Keep looking up. Chuck, why the emergency call to my hotline?
Because we left off a place that has really put me in my peak curiosity.
Okay.
Which is, we were talking about how the death of stars seeds the universe with the ingredients of life, which, by the way, was like just incredible. What a great explainer, where we talked about how fusion leads to a point where we get to iron, we can't go anymore, or as I like to call it, absorption. And
absorption.
Then, and then boom, we have to explode, right?
Yes.
But then this is what got me when you said that, and then that is when these elements go out into the universe and they seed stellar nurseries and they start this process again. And I'm just like, how does that even happen? Like, how does the process itself then get kickstarted,
Okay, so a couple of things. Let me come into that from a back door.
Okay.
So if you take biology class, and every biology class will spend some amount of time trying to define life.
Yes.
Okay. And it's hard because we only have one example of it.
Right.
So it's hard to generalize what life requires if you only have one example of life. The day we find another example of life, We can throw away the things that we thought were fundamental to life that happen to apply to us and just get the basic common denominator of the 2 life forms that we know about. And if we discover a 3rd life form and a 10th life form, we can more sharply tune. So, for example, does life need liquid water? Well, we know life on Earth needs liquid water, but does all life? Maybe there's liquid ammonia in another place, okay? That matters. I saw a comic where there's a crashed alien flying saucer in the desert, right? And the aliens are crawling out, and they're saying, ammonia, ammonia. So just a little bit of a cosmic perspective there.
Right.
So life, I don't think we know. But often what's bandied about is the idea that life has a metabolism, okay? It uses energy. It needs a source of energy so that it can use the energy. And then when it uses the energy, it has to continue to replenish the source. And life needs a way to reproduce itself. Otherwise, it wouldn't sustain. I guess something can be alive but not ever reproduce itself. But in the full understanding of what life means and does on Earth, it has a metabolism and can reproduce itself. Okay? If you look carefully at stars, they have a metabolism. They're born, they live out their lives, they die, and they reproduce themselves. So by some definitions, even many definitions of life, stars are alive. Just putting it out there.
So in the respect of life itself, there is a facet where stars themselves fit the definition
Fit
the
some of those
definition of
very
being alive.
important definitions. That's correct. And the reproducing themselves is their gas clouds waiting for this enrichment that then birth a next generation of stars. So it's just an interesting way to think about stars relative to how we've thought about biology. So now we can ask how you make a star in the first place. All right. Well,
first you got to get a good agent. Let me just tell you, because you can have all the talent in the world, but if you're not connected correctly, you're going to have some issues.
okay. So some gas clouds have better agents than others.
Okay.
All right. So there are 2 broad categories of galaxy out there. One of them is elliptically shaped, and we call them elliptical galaxies.
Okay.
And they're sort of round, and they don't have much gas at all. They ate up their gas back when the galaxy was born, leaving hardly anything left to make new generations of stars. Okay? We call those elliptical galaxies. And broadly again, another is a very flat version of a galaxy that has spiral arms, and we call those spiral galaxies. All right? Very clear and present. All right. Those are very inefficient at making stars, and they're still making stars today. They're as old as the elliptical galaxies, but they're still making stars, and they still have huge repositories of gas. All right. Now, I have a gas cloud minding its own business.
Okay.
All right. There are reasons why a gas cloud would just be happy to stay that way its entire life. But here's what happens. Either a star blows up nearby, creating a shock wave that literally shocks the gas cloud.
Okay.
Or there are other sort of waves that relate to the maintenance of the spiral pattern, and they're called spiral density waves. And the point is, what we have is you have gas clouds moving through a region of the galaxy that, because of this, what's called a density wave, it's compressed as it moves through this region before it comes out the other side.
Gotcha.
All right? Okay. And so what's an example of that? If you're in traffic and you're driving down the street,
Right.
and then you sort of, if there's a slow-moving car with its flashers on,
Right.
it slows everybody down.
Yes.
Okay? And you work your way around it and come out the other side.
Right.
That's a density wave in the traffic.
Awesome.
If you see it from a helicopter, the entire traffic pattern is moving because the car with its flashers on is moving. It's just moving slower than everybody else. So the traffic is moving fast, it slows down, and emerges out the other side. That is a density wave in the traffic. It's a perfect analogy to what's happening in the galaxy, except the galaxy doesn't have cars. All right. So here's what happens. If you shock the gas cloud or create a density wave that'll force some compression, little bits of it will now be denser than other regions.
Okay.
If you're denser, you have stronger gravity near your surface than other places do. Well, I want to get that next molecule that comes by, and you're going to attach to me. You're not going to be free floating anymore. Okay? So, all right, I just added a molecule to myself, and you didn't. With every extra molecule, I now have more gravity than I had before. Okay? And I start clearing out the gas cloud, because even if you tried, if I started before you, I'm going to win, because this is a runaway process. For all the new mass that I accumulate, based on the power of my gravity from before, I now have even more gravity.
More gravity.
Correct. So more gravity breeds more gravity. And this is a runaway process. And so when this happens, you can trigger star formation in a gas cloud. And typically, there's a whole region of the cloud that starts making stars. And when you do that, you make a star cluster. All the stars with the same birthday. And it's fascinating how we use star clusters to figure out how stars evolve. It's more fascinating than it sounds like than I'm even explaining to you right now. It's just complete. It's the same thing as taking a snapshot of civilization, and all you have is a snapshot. And you have to figure out, well, how are people born and how do they die? You know, are you born, are we born in the ground?
Right.
Shriveled, and we bring you out of the ground, and then we feed you, and then you flesh out, and then over time, do you then shrink and then exit back into another human being? The time order is not obvious, because we don't have a video of this happening. We just have, because we don't live long enough, we just have snapshots of clusters at different stages of their evolution. And so that's another explainer. I'll get to that. It's very cool. But I'll give you an example. Everybody in a day goes to the bathroom, one way or another, but you don't spend much time there.
Well, that's debatable. Debatable. Just saying.
Relative to other things you do, you don't spend much time there.
Okay.
So a snapshot is not likely to catch you in the bathroom. Do only some people live in the bathroom while others don't? Or does everybody go through the bathroom? So these are questions we ask, and we answer them brilliantly in the history of this exercise. But my point is, this triggering of the gas clouds is what, this shocking of the gas clouds is what creates pockets of condensation, pockets of convergence of matter that then, as they continue, they get bigger and bigger and bigger. Now, it'll keep doing this. The native temperature of the cloud will sustain it to some level, okay? But as it gets more and more and more massive, there's greater and greater gravitational pressure on the core. There is the point where we have ignition.
Got you.
Thermonuclear fusion. Ignition. And in that moment, a star is born. And so that then stabilizes this against any further collapse. And it will continue to accrete material unless the star is of a very high luminosity variety. Because you know what happens? The photons that come out, they exert a pressure onto themselves. And if you're Johnny-come-lately to the party, you just get pushed away. And so this is a fascinating point in the evolution of a star, because the high mass stars, we see them evacuating the pocket out of which they formed.
Oh, wow, yeah.
Pockets where the gas is not as dense. Because first it had absorbed up the initial amount of gas in that pocket, and anyone who tries to make it later, it ends up getting pushed away.
Sorry, guys. Club is full.
Club is full.
Club is full, guys. I got to put the rope down. Got to put the rope down, guys. Listen, now I'm a big fan. Don't worry, man. I saw your latest work. I'm a big fan. But the club is full, man. We got fire laws. Man. Sorry, no, put your money away, bro. Put your money away. I'm serious.
And by the way, this is decades and decades of hard-earned telescope observation, brilliant people thinking about what's going on. There's the thermodynamics of it, the quantum physics of it, the chemistry of it. There's all of this going on. And that's why in astrophysics, we tap the expertise from people of many different professions. And that's also why astrophysics is, by many, myself included, is considered a gateway subject to teach in school.
Ah, so you can use that as a means of going to, and as a portal to go to many different lands in science.
Yes, in science. The biology, the chemistry, the physics, the
geology, whatever.
The geology on the planets. And, of course, we send hardware out there. So if you're an engineering geek and love the universe, we got a place for you, too. So
nice.
Yeah, this has been my recruitment PSA for modern astrophysics. So anyhow, that's kind of
how it's done. That's pretty cool. I love it.
A fast addition, Chuck. Do you know when I was in high school in my chemistry class? I had asked, as we learned about the periodic table, I said, "Where do all these elements come from?" They said, "Well, we find them in the Earth." That was the answer. It would be a couple of years later when I learned, no, we made these in our stars.
Right.
Okay? They were birthed in stars first, and then became part of the Earth as the Earth formed. By the way, borrowing a bit from the earlier explainer, where the buck stops at iron.
Yes.
All right? And by the way, there's no shortage of iron in the world and in the universe, and Earth's core is primarily made of iron.
Mm-hmm.
All of that comes from the fact that once the star made iron, there it is. It's a major part of that process. And it makes the heavier elements. It can still make heavier elements. It's just not getting energy out of it. Right? So there's plenty of energy in a supernova explosion to keep making elements up the periodic table. But you're not sustaining the energy of a star by doing it. You're sucking energy from the explosion and all the energy that's already available to you. So,
man.
Anyhow, that's how it works, Chuck. How that works.
That's fascinating. I love it. It's, it makes perfect sense. And the thing that's weird is that you have to think about these in terms of atomic terms. Like while you're thinking, I'm trying to think about this, not in terms of like actual things fusing like Lego, right. You know.
Legos are good. That's a good fusion. Because you get them close enough, then they just stick.
Right.
But they stick in there.
But it's
it's happening at a not only atomic, but a nuclear level.
Nuclear level.
By the way, the whole universe, which was all energy at one point, as the universe cooled, that E equals mc squared, the energy becomes the matter out of which everything would later form. And most of that matter is hydrogen and helium. So you start out for free from the birth of the universe with the hydrogen and the helium and these big gas clouds. They're just there for free. That's all.
Wow.
Yeah.
Oh, man, this makes me just want to go just be there when it happens. Why can't we just be there and
let the world know that Chuck wants to be in the room where it happens. Chuck wants to be. I just want to be in the room.
I just want to be in a room where it happens.
Is that the name of that song? What's the actual name of that song? It's from Hamilton.
It is from Hamilton. I don't know the name of the song.
In the room where it happens.
Yeah.
Okay, we'll work on it, Chuck. Maybe
all right.
I'll hook you up with the universe one day.
Yes, exactly.
All right, another Star Talk explainer. Good to have you, Chuck.
Always a pleasure.
For Star Talk, Neil deGrasse Tyson. Keep looking. Guys, I've got a Star Talk Sports Edition explainer. This one about golf, lip outs in golf. Gary, I think we're going to have to muzzle Chuck for this. I don't know. He's highly golf opinionated, and I don't know. No telling what he's going to say.
All I do is speak the truth. That's it.
I don't get the feeling Chuck's clubhouse friendly.
It's true. Oh, wait, why? Are we playing at Augusta now? What is what is going on?
All right, let's get back to lip outs, people. Okay. You know, I see golf. I'm not a golf player. You know, I just always imagine the conversation between a golfer and a baseball player, right? And just how that would go by. So the baseball player says, you want complete silence when you hit the ball? I say, yeah, we need silence. And they say, well, how fast is the ball moving? Well, not at all. It's stationary. Well, where is it? Oh, it's right between my feet. And so you need silence? Yeah, that takes concentration. Well, how about you? Oh, well, our ball is moving 90 miles an hour, thrown by someone who doesn't want me to hit it. And so,
while I'm being booed.
While 50,000 people are screaming at you. But what we all know is that certain golf, typically a putt, but it can happen on any shot. The ball will hit the rim of the cup and then spiral around and pop out. Frustrating for the golfer because that's a lost shot right there.
It's a stroke off. Yeah,
it's a stroke off, and
right. Yeah,
no,
that's a loss of a stroke. Okay.
Yes, thank you.
We'll go with dropped shot, shall we?
Yes.
Drop shot, fine.
Yeah.
So it's so what's interesting about it is it can happen almost no matter how far away you are from the cup. There are good videos of compilations of lip outs where some guy was like a couple of feet away and he taps it in, but it lips out. And then everyone says, oh, and then he just goes around a little cocky, said, you're going in this time, bop, lips out again. And so he lost 2 strokes when the ball was within 2 feet of the cup.
Yeah, I think call that you suck. Pretty sure that's the golfing term.
That's the official.
The official golfing term.
See, I mean, if anyone's watched Caddyshack the movie, they know it's a gopher in the hole that's pushing the ball.
The gopher. I forgot about the gopher.
The
gopher is at fault for all of it. Yes. So here's what's going on. You think you're hitting the ball straight, and you are, and so the ball has what we call linear momentum. So it's momentum in the direction it's headed.
Yeah.
However, if you do not hit the ball exactly towards the center of the cup, and it sees the rim of the cup, it's like you reaching out to like a maypole as you're trying to run by it, grabbing it, and what happens to you?
Ooh, you get to swing around.
You swing around. So all of a sudden, your linear momentum, okay, right. What you think is purely linear momentum also manifests as angular momentum around the pole. Okay? So that happens. You reach out and grab. So when the ball sees the depression in the cup, that's effectively falling towards the middle of the cup. And so there's angular momentum there that is getting picked up as it goes around the center. And depending on how fast the ball is moving and how much on the lip it was, it'll either swivel and go in or swivel and pop out again. And so the only way to avoid this on every single shot is hit it directly to the center of the cup. That's all. To the center of the cup, and it drops in.
Does it matter on how much? Is there a critical mass of the ball that must be below the lip of the cup?
Oh, very good point. So I'd have to do a calculation on this. Right. But I would say if you got half the mass of the ball below the lip, that it's going in.
Yeah.
And because it's very hard to all of a sudden have a force vector pointing upwards while this is happening. By the way, unless the ball is spinning, okay, depending on which way the ball is spinning, if it's spinning, it can actually crawl out if that's the direction the spin is going.
That happens in basketball where you see the ball ring around.
Well, so in basketball, lip outs are every third shot, right?
Yeah.
I mean, when you think about it.
Yeah, it rings around and then it gets thrown out. It's actually in the hole. You know, it's in the cylinder.
Well, I haven't seen it. Find me one where it's half already in the cylinder.
I
don't think it.
Come on now. Yes. I don't think more than half, but definitely it's in the cylinder. Yeah.
Up to half. Oh, yeah. Okay.
Up to half.
In there, but it's touching the side. And depending on the spin, the internal angular momentum the ball had by your shot, that'll affect what it's going to do as it kisses the rim.
Yes.
All right. And so some shooters will give a backspin when they hit the back of the rim. So then the spin takes it in with that much more vigor. But if you have different spins and you hit the rim in the wrong way, it's going to spin in a way you don't want. You're not going to make the shot. So the same is true in golf. And in golf, the spin on the ball matters, right? For so many of those shots, particularly ones that are onto the green, you don't want it to keep moving and rolling off the green. So many of them have backspin.
Particularly bunker shots, Neil. If you found yourself in a sand trap, you've got to get right underneath the ball, flatten the face of the club, and then you impart the backspin on it, so as it doesn't overrun on a fast green, and then will spin and drop, and then that will be the
exactly.
rotation.
And golfers are excellent navigators of subtleties in terrain, so that if you're going to do a backspin, you're going to do it on the
high side.
On the high side, so then it rolls back down. So you're going to think this through. Well, you'll do it even if it goes low, right? You especially need it if it goes low, because you don't want it to then roll off and go into the pond or into the brush. So all I'm saying is that the only way to avoid it is to send it straight in.
So remind me again, why when it looks like it's going to go in, it rises up? What is elevating that for it to lip out and not lip down? Okay,
so what you're saying is it's already partly in the cup. Right. So what's it doing? So it has so much momentum, right? The question is, how is that momentum going to manifest? Okay, and so as it comes, so let's say you're going to lip left to right and out. It goes in. So what's actually happening is it's almost like the bank of the track in NASCAR.
Oh.
Okay, think about that. If you come to, in fact, why don't we talk about banks in NASCAR in the next segment? This is a nice lead into that. So here I am in a car, and if I'm driving too fast on that bank, okay, I can tell you now, if you drive 300 miles an hour into a bank, I don't think the rubber in the road is going to hold you to the bank. And it looks like, you should just fall into the middle. You're just going to fall in. No, you're going to fly right out, headed the other direction on the other side of the track.
Okay, so we're imparting that theory into a golf ball as to why it rises out of.
Correct. Because when you're in a car and you're on a bank, you feel this force sort of pushing you outward, right? Depending on how fast you hit that bank. And in fact, that's what helps keep you on the track, provided you don't take the turn too fast. So all we're saying here is that on that turn, if you have enough momentum, then that momentum will continue to carry. And the fact that the ball was a little bit in won't matter, because it's seeing because by the way, it's not in the cup when that happens. It's on the part of the grass that bends in.
It's on the lip. Yeah.
It's on the lip. And on that lip, it's not a perfect 90 degrees, right? It's like,
it's a small, tiny little bank.
Tiny little bank. It's a tiny little bank between the grass and the turf and where the cup begins. And that's the bank where this thing flies out on.
Now, if only we could get that ball to do what the car on the bank does, which is fly out and then explode in a fiery ball of death, I would watch golf. I would watch golf. That would be amazing. Finally.
We'll talk to the authorities on that one. Right.
Oh, dear. Can't see this taking off on the Golf Channel, can you?
Oh, I certainly can. Exploding golf? Oh, my God, I'm watching that.
Well, we've all seen clips of practical jokes where the ball is something that explodes on it, not explodes dangerously, but just pulverizes on impact. We've seen that, right? You make a golf ball out of chalk or something, but you don't. The person doesn't know it. You're the one who puts the ball on the ground waiting for them, and then they hit it, and then it's just a puff of smoke.
That right there is eminently more entertaining than actual golf.
Do you get
that's
the
all I'ma say. That's all I'ma say. That is more entertaining than actual golf.
Could we get whisper commentary though?
Oh, that'd be so awesome. Just like he's addressing the ball right now. It's a beautiful day here at Augusta. Winds are out of the southwest. I see the ball is on the tee. As he approaches the ball, here's the backswing. And oh my God! It exploded! What the hell just
happened? Okay. I'm sure Chuck's agent the phone is ringing off the hook to get Chuck to comment.
Come on, that is awesome. Exploding golf.
So if any of our audience are listening or watching this and they play golf and they lip out in the future, it's not because you suck. It's just because of science.
Science.
Right.
And by the way, of course, the ball can like bounce in and bounce off the bottom of the cup and bounce out. That's not lipping out.
Yeah, but that's whoa. Now you just, I got to know now. Maybe you know or not. Let's say the ball does pop in, like it's bouncing. Bounces in the cup.
And back out, yeah.
Bounces back out. Is that still considered, it touched the bottom of the cup?
Yeah.
Is that a shot made, or do you have to then put it back in the cup?
Have you sunk that? Is that technically a sink, or whatever you call it? That's
whatever. Yeah,
because the cup is metal, isn't it? So there's every chance.
It's tin. Tin cup,
metal,
as they say.
Yeah. So if it falls vertically, then there's a chance
it could pop back out. That's what I'm saying.
It could pop back out
if it's a high enough arc on the bounce. And it ends up falling directly into the cup, hitting the bottom, and then popping back out.
Right.
Is that now a shot made?
It just needs enough energy to bounce even bounce a couple of times.
We need
back
officials. Out. We need golf officials.
I'm suspecting the ball has to still be in the bottom of the cup when you reach in there.
Oh, see, that is cold-blooded, man.
Yeah.
No, just become a better golfer. That's all, Chuck.
I put it in the cup. How much better can I be? I mean, God. That's kind of like if the ball has enough arc where it falls through the basketball hoop, which is highly unlikely, but then somehow bounces back up through the basketball, you still get the 2 points.
Oh, so you're talking about it falls through the hoop, bounces off the ground, and goes back up through the hoop, and
you still get
out.
2 points. As a matter of fact, they should give you 6 points, but you still get to keep.
Can you imagine how high you would have to be to get the rebound to go back up through the hoop?
You would get the 2 points on that, Chuck.
You get the 2 points, right? Yeah, so that's what I'm saying. Like that's
no, I know. The new rule. If it goes backwards through the hoop, it subtracts the points.
That's just wrong.
Okay, so our crack team of behind the scenes researchers has confirmed that a ball that bounces out, that counts as a stroke.
Okay, so you don't get this. It's not over. You still got to play that ball.
Correct.
Oh, that's terrible. This is why I hate golf.
Okay, we should rename this Reasons Why Chuck Hates Golf. Not enough explosions, number one.
There you go, starting with that. That's the Michael Bay reason. Not enough explosions.
And not enough chase scenes, yeah.
Right, no chase scenes. And if the ball bounces in the hole, which is the whole point of the game, if I actually achieve the objective of the game, which is to put the ball in the hole, if the ball comes back out of the hole, then the objection is I have not completed my objective. So,
all right. So now here's another thing. If you want the spin on the ball to help you not get a lip out, if you give a little sort of, I don't know if you can do this with a putter, but surely there's a way. You give it a slight sort of backspin, very slight. Okay. So that when it begins to lean into the cup, the backspin takes it down into the cup.
Right on.
But if you give it front spin, which would normally happen if it's sort of rolling in a normal way, it has front spin as it goes in. But you can disrupt that a little by subtracting some of that front spin. So the ball is skidding for part of the way. You can do that, all right? But if you give it front spin, then that sucker is just going to want to. I've seen some lip outs where it's gone twice around the hole before it came out. So, yeah.
Okay.
You got it. So that's lipping out on the golf course. Now haven't we done other shows about the science of golf clubs and things? I think we have.
Mm-hmm. Yeah. We need to do a show called Golf Sucks. That's what we
No, stop. Guys, that's all we have time for. And Gary, Chuck barely behaved on that one. Just barely.
Chuck's Chuck.
Truth to power.
Chuck is Chuck.
It's truth to power, people. That's all it is.
All right. Star Talk Sports Edition Explainer. Neil deGrasse Tyson here. So this will be a benchmark day. We'll look back on that fondly. So Chuck, what's been bugging you lately?
I'll tell you, I don't know if it's bugging me. Maybe I'm happy about it. maybe the entire human race has something to be hopeful about. You know how I feel about climate and the climate crisis.
Right.
But so I wake up this morning and it's all about fusion. Fusion everywhere. Everybody's talking about fusion. I'm like, whoa, is this a good thing? Or are they yanking my chain? Are they just making me, what are they doing? Are they doing the Lucy pull the football away from me? What are they doing? What is happening? What is happening with the fusion?
Oh, okay. So the highlight is at one of the national laboratories, Lawrence Livermore National Laboratories, where they among all the national labs are, one of their major tasks is as shepherds of our nuclear arsenal. Okay, the nuclear fuel, basically. So radioactive materials that might be used in weapons, and it is funded by the Department of Energy, not the Department of Defense. So that in fact, the total amount of money we spend on defense is not only the DoD's budget, but an important fraction of the Department of Energy's budget that involves weaponry, basically. Okay.
Right. Yeah.
So there they have the world's most powerful laser. And what they do with a bunch of these lasers is they aim them all at a tiny target and they cause the target to explode. All right. That alone is not okay.
Sounds like America so far.
You'll say, well, what's new about this? Because we've been blowing shit up for like forever. So if the target is uniformly heated, evenly in all directions, and the material is very uniform in all directions, so there would be a spherical shape, then the explosion creates an implosion on the other side of that explosion, right? You can't just have stuff come out unless the Newton's law for every action is an equal and opposite reaction. So the explosion that comes out creates an explosion that points inward. And that creates very high pressure and very high temperature. And under those conditions, you can take two atoms, light atoms, and merge them into a heavier atom.
Sweet.
That takes a lot of high temperature to accomplish. Because let's take the lightest atom of them all, which is what?
I don't know, maybe hydrogen?
Hydrogen, you got it. So hydrogen in its nucleus has one proton. And helium in its nucleus has two protons. Plus two neutrons. So how am I going to create a helium atom from a hydrogen atom? So you got to get a bunch of hydrogen atoms together. All right. Together. Well, here's what no one is telling you in the news, but it's obvious when you think about it. What do two protons want to normally do? They're both positive charge.
They don't. They like each other, but they don't like each other because they're alike.
Okay.
It's like when you meet somebody at a cocktail party and they remind you of yourself, and you're just like, I don't like that dude. I don't really like that. I don't want to be over there talking to that dude.
Chuck is still in therapy, people. Just so you know.
I know exactly. It's like, it's a simple question, Chuck. Where did cocktail parties and liking people come in? Yeah, but they want to get away from each other, right?
So these are like charges. So in the case of two protons, they repel each other. So how do you get them to come together as a new helium nucleus if they want to repel? So this is like rolling a ball up a hill, all right? If you don't give it enough energy, it's not going to reach the top. It's not going to reach the top. Okay.
There you go. So
if you roll it faster and faster, giving it more and more energy, eventually the ball will reach the top and tip and go over and fall on the other side of the hill. That is precisely what's going on with two protons. Here it goes. The two protons want to come near each other, but they repel. let's boost the temperature, which speeds everything up. They get closer to each other before they repel. Boost the temperature some more. They get even closer. There is a magic temperature at which these protons will come close enough so that an entire new force operates. It would have to be a strong force in the nucleus to keep two protons together. In fact, the name of that...
quantum love. That's called quantum love.
Oh, where's that disco? So I remember Jungle Love. Remember Jungle Love? We know quantum love.
Jungle love.
Yeah, quantum love is like
quantum
you resist
love.
until you cross over the barrier, and then you're there. So when they cross that barrier, a strong force that operates in the nucleus takes over. It's one of the fundamental forces of nature, and it's called the strong nuclear force. There it is. Okay. That's what it's called. It is a very short range force. It only operates on scales as small as the nucleus itself.
Wow.
But you have to get there for it to grab a hold of you and make a new atom. That's why it takes high density, high pressure, and high temperature to overcome this.
All right. So
that is
I'm with you.
That is thermonuclear fusion. Thermo is hot. Nuclear is the nucleus. Fusion, they're bringing it together. It turns out that when you do that, your products have less mass than when you started with.
Whoa.
Oh my gosh. Where did the mass go?
Exactly.
E equals mc squared. My lovely. So the mass on the one side of the equation, if you lose it, it manifests on the other side of the equation as energy.
There you go.
There it is. And so they manage.
That's fusion.
So at the Lawrence Livermore Laboratories using lasers, and by the way, they've led the world in lasers like for decades. In fact, people on the inside call it lasers, and lasers. Okay, Lawrence Livermore National Lab. Okay,
lasers, and lasers. That's
and lasers, right. So anyhow, so they have managed to. You can add up how much energy it takes to turn on the lasers and fire them, and then look at how much energy comes out after you've done this. And they got 50% more energy out of this than the energy of the lasers that went into it.
That's amazing.
Amazing. First time that's ever happened.
Now that's an energy source now, because you got more out than you got in, which is what I want to know. Which is, so what did it take? What would it be? What did it measure? Like, is it anything significant? And percentage wise, that's great. But like, what would it take to turn this into an energy? It would have been great if it just
broke even. That would be a major milestone unto itself, right? But the fact that they got 50% more energy out than they put in, it says, oh my gosh, we can get the physics to succeed. And for my money, I'm saying if the physics works, then it's just a matter of time before engineers say, I got this. I'm gonna make something out of that. I got this. And so
that's amazing.
Yeah. And so I'm very much look forward. There's a civilization pivoting on this result. And by the way, what I just described to you, the sun does every moment of its life. The problem over all these years is that, of course, we've known how to make fusion. We've known how to make fusion since 1949 or something. When the first fusion bombs are called hydrogen bombs. They're using hydrogen. That's what I just told you. Two protons is merging hydrogen atoms, nuclei together. So we've known how to make fusion forever. The challenge is not how do you make fusion, how do you control it?
Yeah, because you don't want the electric company having to move to a new city because there's no city left.
Right, exactly. So while in America, we're really good at blowing stuff up, we're less good at controlling that explosion, right? So the Holy Grail was, can we undergo fusion in a controlled way where one day you might be able to throttle it or contain it or transport it? And we'll finally get maybe that ending scene in Back to the Future.
Right.
Here's your cue, Doc.
Marty, it's your kids, Marty.
And do you remember how, and Marty says, yeah, but Doc, where are you going to get the energy? There's no lightning bolt and there's no room for, what are you going to do? And remember what he does?
He dumps a bunch of trash into the flux capacitor, which is now powered by fusion.
It's Mr. Home Fusion, right? It was like a blender.
That's right.
He puts it in, and that undergoes nuclear fusion. And so one day, perhaps, we'd have fusion reactors in every car, and then you could
wow,
there it is. So this would transform civilization, even. Regardless of the carbon footprint that it doesn't have, it would transform civilization. But it also happens to not have a carbon footprint. So we could stave off this growth of fossil fuel burning and greenhouse gases. And we'll still have to recover from the damage we've already done, because a lot of the carbon dioxide got uptook into the oceans. And if you start removing it from the atmosphere, it begins to come out of the oceans, and it'll do that until it becomes equal again. So you got to recover that. But it is the future. And just I tip my hat to the physicists and engineers at the national labs. And this whole thing was important enough. It was a press conference announced by the Secretary of Energy. So, we're chomping at the bit.
So then it is good news.
Good news. I suspected accurately. Yes.
All right.
And we've been at it for decades. Just thought I'd tell you that. And so this will be a benchmark day. With the first and second week of December in the year 2022. We'll look back on that.
Another day in December that will live not in infamy. What is it when it's a good thing?
Femi.
Just Femi.
Live in Femi. Okay. All right, Chuck, we got to end it there.
All right.
But there's way more about fusion. That's another show. We'll talk about stars.
Yeah.
There's more and why stars explode. All right. I'll leave a teaser here. You ready? Fusion, you get energy by combining little atoms. Fission, you get energy by splitting big atoms.
Okay.
But wait a minute. There's got to be some point in the middle where these two phenomena meet. What happens then? Therein are the seeds of the undoing of great massive stars in the universe. That's a whole other explainer we'll get to. Oh, yeah. Nuclear fusion in a nutshell. This has been yet another Star Talk Explainer. Great to have you join us, putting fusion back on the map. Chuck, always good to have you.
Always a pleasure.
Neil deGrasse Tyson here. Keep looking up.